This is chapter 9, and we're going to be focusing on calculations from chemical equations. Now we have to remind ourselves of molar mass. Molar mass, or another word for it is formula weight, has the units of grams per mole. All right, you can see those units right here down below. Now we're going to be using molar mass as a conversion factor, and that means we're going to use it to go from one thing to another in an equation. So just to remind you how to calculate molar mass, if we did C5H10O5, we take the amount of each atom, we multiply it by the mass found on the periodic table, we add it all up, and in this case we'd get 150.13 grams per mole. Now remember that grams per mole is utilized here when we talk about it in terms of grams per mole, and per mole means per 1 mole. So we can write it that way, or we may see it written in the flipped way. And again, both of those are acceptable conversion factors. So you're going to see that being used today a lot. Now, something new for you is what we call stoichiometry. And this fancy word really means going from one thing to another in a balanced equation. So here we have a balanced equation. Actually, I meant to highlight that here. We have a balanced equation. We have 2H2 plus O2 yields 2H2O. And the main components we're going to be looking at in these equations are the numbers in front, and we call these coefficients. Now, if you don't see a number in front, that is an assumed 1. So we're going to be utilizing that often. So again, we're going to be using the coefficients to create conversions. So you can create conversions by writing out any value. So putting the 2 from here and the H2 from here, and then using that as a conversion to O2, or even writing it flipped if it's necessary. The 1 from the O2 and the 2 from the H2. Now those are just examples using it when it is a reactant. Okay, but we can also create these relationships when we talk about products as well, so what we say across the arrow. So we can write relationships between, again, 2 moles of H2 because of the 2 here, and then we can also talk about H2O. We just have to utilize these coefficients. Okay, and I gave you some examples of these conversions below. Now the first thing we're going to do when we study stoichiometry is really focus on mole to mole conversions. All right, and again, we're going to be relying on the coefficients in front of each reactant and in front of each product. Now, a quick little review from last chapter here. I have a question right here. What type of reaction is this? So what reaction is known to have CO2 and H2O as its products? Hopefully you said combustion. So again, that was from the previous chapter. So we're going to focus on this equation. We have C6H12O6, which we're going to learn is glucose. We have oxygen, and we call that molecular oxygen because we have this 2 here. We have CO2 as carbon dioxide and H2O as water. And our question is asking us how many moles, so we're looking for moles of molecular oxygen, are needed to react with 10 moles of glucose. So when I do a problem like this, I like to actually write down what I am looking for. So let me show you. We're looking for moles of molecular oxygen. So I'm going to put a little question mark, moles. That's what we're trying to find, this compound. And what we are starting with is 10 moles of glucose. All right, so the one that has the number underneath it is what you start with. You always start with what you're given. And then what you're going to end in is the one that has the question mark. So we're going to start with 10 moles of glucose, and I'm going to actually write that as C6H12O6. Now, what you have to be better at in this chapter is units and what we call identifiers. So every single component of your dimensional analysis needs a unit and an identifier. Okay, or the compound you're referring to. So just like we've been doing from the beginning, moles is on the top, so moles is going to go on the bottom. But now it's not only moles, but it's moles of glucose. Or you could write C6H12O6. Either way is fine. So what you're leaving goes on the bottom, what you're going to goes on the top, and we're trying to go to moles of O2. Okay, so what you're going to on the top, what you are leaving on the bottom. Okay. Now, where do we get the numbers for a mole to mole ratio? We get them from the coefficients. So we just have to see here, we have the number in front of this and the number in front of this. So the number in front of the C6H12O6 is actually just a 1 because you can't see anything in front of it. And what's in front of the O2 is that 6. So that is how we go from one thing to another. We have to be in moles, and then we have to use the coefficients. So to do this math, you truly just do 10 times 6, which gets you 60 moles of O2. Okay? So all answers now need to have the number, the unit, and the identifier. You will no longer just be able to put the unit. Okay? It has to be the identifier as well. All right, let's do another one. How many moles, is what we're looking for, can be produced from 2 moles of glucose? So you always start with what you're given. Since you're in moles, you can dive right into a mole ratio. So the thing that you start with always goes on the bottom. Now, if you feel more comfortable by putting a 1 underneath just to see the fractions in the numerator and denominator, go right ahead. And what you're going to, which is what you're trying to end in, goes on the top. Okay? Now, where do you get these numbers? From your coefficients here. So my coefficients for this one is a 6 for the CO2 and another 1 because we can't see anything in front of the C6H12O6. And then my answer for this one is truly just a 2 times a 6. You multiply when everything's on the top. So my answer is 12 moles of CO2. Okay? So mole to mole conversion. Now, what if we add in mass? So I want to quickly remind you of our last chapter, what I called the mole train station. So moles and atoms, and remember, atoms could be called molecules or particles as well, but we're going to mostly focus on atoms, so I'm just going to use that. And we used Avogadro's number, which you know to be 6.022 times 10 to the 23rd. But what we're focusing on in this chapter is grams to moles, and we used molar mass, which we reviewed at the beginning of this PowerPoint. So we're going to be focusing a lot on this conversion from grams to moles and back. So calculate the mass of H2. So we're trying to find this mass, or you could just write grams, whatever works for you. Produce when you start with 6 moles of aluminum. I like to write all my information. Now you always start with what you're given, and I'm given 6 moles of aluminum. Okay? Now I cannot go from aluminum to H2 without being in a mole ratio. So I'm going to leave the aluminum by putting it on the bottom and go to the H2. Even though it's called hydrogen, we need to know there's 2 H's in that. We're going to use that a little bit later on. Now, where do I get the numbers for this? I get them from the coefficients. So you look at the H2 and you look at the O2, or excuse me, the Al, and you go ahead and fill in those numbers. So this 2 is going to go over here, okay? And this H2 is going to be from right here, okay? Now, the question is asking us for mass. If we finished right now with our math and did the math, we'd end up in the unit of moles. We need to now do a second step, all right? So we're going to, whatever we're leaving, we're going to put on the bottom, and what we're going to, we're going to put on the top. Now, when you go from moles to grams, you will always, always, always put a 1 under the mole. You only use the coefficients, these front numbers, when you're doing a mole to mole ratio. Only here. You will always keep a 1 when you're doing a moles to gram. Okay, so that is a very common mistake students make. Now, what you're going to fill in here is the molar mass of the H2, which is 2.02. Okay? Now, we're going to go ahead and do the math. Let me tell you what I would do in my calculator. I would take 6. I would multiply it by 3. I'd then multiply it by 2.02. I'd get an answer. I would then divide by 2. Of course, there's multiple ways you could do this, but try that and make sure that you get the same answer as me, which when I round it to sig figs ends up being 18.2. But we now need grams and a unit identifier here. Okay, and to be honest, I'd probably put that grams right next to it, but kind of ran out of room. There you go. Okay? So we went to moles, did a mole conversion, then we went to grams. You have to do this mole conversion to go from aluminum to H2 in a balanced equation. Must have a balanced equation. Let's do another example. How many moles of water, so I'm looking for this in moles, if I start with 325 grams of octane? Okay? And I'm going to always start with what I'm given, 325 grams of C8H18. I don't want to just see grams. I want to see grams of the identifier. Now, I cannot go directly into a mole ratio because I'm currently in grams. To do that new mole ratio step, I have to be in moles. So I have to go, I wrote that as it should be an 8. I have to go first from grams to moles. And how do we do that? We keep writing, wrong number here. We have to do molar mass, okay? So when we calculate the molar mass of C8H18, we get 114.26. Again, yours may be a little different if you used a different periodic table, but hopefully close. And again, that 1 goes here because of the mole to gram relationship. Now I can dive right into that new step, my mole ratio, and go from what I started with to what I'm trying to end up with, okay, which is 18 is going to go here, and the 2 in front of the C8H18 is going to go there. Now, since I want to end in moles, if I finish right here, I'll end in moles. You end up with whatever's on the top of this last step, okay? So if you finish your last step with the units you need, you will be doing it correctly. All right, now, after I did the math here, I got 25.6. Please, please, please do the math to make sure you're doing it correctly, and please ask if you're not getting that same answer. Okay? All right, now, let's do a grams to grams. So this one's a little bit different. We're going to have to add an extra step. So let's see. How many grams of CO2 can be produced from burning 25 grams of octane? So you start with what you're given. And we're going to go from, we cannot do that mole ratio until we go into the moles. So I'm going to do that same thing. I'm going to use molar mass, and we actually just used that in the previous example, so it's nice to be able to utilize that again. Then I can dive into my new step, the mole ratio. Remember, the unit you are leaving on the bottom, the unit you want to finish up on the top. And we're going to carbon dioxide, which is why it's nice to kind of have everything written under here so you know what you're going to. 16 and 2. And then we are going to finish us off. We would typically stop here, but this would end us in moles, and we need grams. So we're going to do one more step. And again, this is about as hard as it's going to get. We have to go back to grams of CO2. You'd calculate your molar mass of CO2, which is 44.01. Again, I added 1 carbon and 2 oxygen, and then I'm going to solve. So how I would do this mathematically is I would take the 25, I'd multiply by 16, multiply by 44.01, get an answer, divide by 114.26, get an answer, divide by 2, get an answer. There's many ways to do this. So if you try a different way and you get the right answer, as long as you're doing it correctly, that's all that matters. Also, I don't want to see separate steps here. I want to see one long step. That is truly what this lesson is about. And also units and identifiers. You can see that I have an identifier on every one of these, and that is what you need, okay? To be honest, I can even add one right here if we want to be consistent, all right? Then you have your final answer. Now we're going to take stoichiometry one step further with what we call limiting reactants or limiting reagents. Same thing, you're going to hear them called both. And basically we have to do 2 calculations, all right? And then we will see whichever one produces the least. And that is going to be our limiting, and the one that produces more or in excess is our called our excess. Okay, these are usually multi-step problems, and I'm going to demonstrate one, and then I have an extra one to show you. Now let's just talk about that term limiting and excess. So let's say we have an equation that you would use in everyday life theoretically. 2 pieces of bread plus 3 pieces of bologna is 1 sandwich. So that makes 1 whole sandwich. Okay, so if you started with 21 pieces of bologna and 10 pieces of bread, how many actual sandwiches could you make? So if I started with 21 of bologna, I would actually make 7 sandwiches, and I used a conversion factor here using my equation. If I started with 10 pieces of bread, I would make 5 sandwiches. So what we do here is we see this is in lesser amount. That means this is truly how many you will make. So we're going to make 5 sandwiches. This then is considered our limiting reactant because this limits how many we can make. And then this is considered our excess reactant because this is going to have leftover pieces of bologna that we can't use. Okay? So that concept of limiting and excess is important to understand to be able to do the problems. Now I wrote you some steps here just in case you need to refer back to them. The first step is identifying a limiting reactant problem or reagent. It's interchangeable. So it is a limiting reactant problem if you have 2 starting amounts of reactant. So if you have 2 starting amounts, so the previous examples we did had 1 starting amount and asked for 1 answer. This is going to have 2 starting amounts. Now on an exam, I will also say this is a limiting reactant problem, but in Gen Chem, if you move on, it will not tell you. Now also, very important, you have to have a balanced equation to do this because you need those coefficients, so you have to have a balanced equation. So again, we're going to start with one of our given amounts, use stoichiometry, which is just a fancy way of saying unit canceling, and we're going to figure out the product in the unit of grams. You're then going to use the other given amount, again use stoichiometry and go to that same product. That is the thing, same one. Now the product that is a smaller amount is your answer. And then that limiting reactant is the reactant that created that smaller amount. Now we're going to apply this to a problem. Makes a lot more sense when you see it. So here we go. We have an unbalanced equation. So that is my first clue is that, hey, I need to balance it. So let's see here. I have 2 nitrates, 2 silvers. Okay, I think we're good there. And again, you can leave those blank or put a 1. Doesn't matter. Now, how do I know this is limiting reactant? Let's see. How many grams of this? So we're looking for grams of AgBr, silver bromide, can be formed when a solution containing 50 grams of magnesium bromide and 100 grams of silver nitrate. All right, so you have 2 starting amounts. Limiting reactant. That's what it should tell you. Okay? So now you're going to be doing 2 problems, 2 separate problems, and you're going to take both of them to the same product. Same exact product, because you have to compare apples to apples. All right, so I'm going to dive into this example here. I'm going to do 50 grams of MgBr. Okay, and we're going to go ahead and we can't do our mole ratio until we go into moles of MgBr. And our molar mass of MgBr, you'll have to calculate that on your own, is 184.13. Then we're going to dive into our mole ratio to what you're actually going to. So what we're going to is what the problem is asking. Now, where do I get these numbers? I get these numbers from my balanced equation. So I have the 2 in front of here and the 1 in front of here. Okay, so 2 because of that, and the 1 because of the other one I highlighted. And then we want to go to grams, because it's easier to compare in grams, and the problem is also asking for grams anyway. Again, we're going to use molar mass, and our molar mass is 187.77. When I do this math, I get 101.98. I know that is not in sig figs, but we'll go ahead and do that in a few moments when we've decided that that is our correct answer. Okay? That's the answer to the one of them. But that only answers this question. We now need to do the other question. So we're going to start with 100 grams of AgNO3. We're going to do that same thing, grams to moles, before we can convert it into our new product. So our molar mass of silver nitrate is 169.88. We're then going to do our mole conversion. And these are actually both 2s, okay, which you can actually, you still want to write the number even though they would cancel each other out, but when you do the math, you can skip them if that makes sense to you. If it doesn't, then you go right ahead and use them. It doesn't matter at all. And we're now in the AGBR. Now, a nice clue is both of these should be the same final grams amount because they're the same product both times when you're doing a limiting reactant problem. You're going to the exact same product. So now when I compare this, I got 110. Now, what the heck does all this information tell me? This is going to tell me what is my limiting reactant. So the first thing I need to do is see which one is less. This answer is smaller than this one, okay? So because the 101.98 is smaller, this is my answer right here. And this is my limiting reactant. So immediately I go right over and I write LR. Now the one that produced a higher amount is then considered my excess reactant. That means there was extra. There's literally going to be extra laying at the bottom of the beaker. Okay? We still need to answer this question. How many grams of AGBR? So AGBR is going to be your lesser amount. So I'm going to actually round that to sig figs and make that 102 grams. Okay? So not only do you have to do this work, you have to answer your final question. Now, you cannot just do one. You will get points for both of these problems because that is the steps it takes to solve this. So don't just think you can do one and give that answer. You have to see which one gives you less, and then you have to indicate that that is your answer. Okay? Now, the last thing we want to look at here is very much simpler is percent yield, and you will need to memorize this equation. And percent yield is the actual over the theoretical. Another way of saying actual is experimental. Now, we've done this in class before in lab. Experimental is what you got or the scientist. Theoretical is what the math gets you. And usually that math is stoichiometry. So this question here is, suppose you have 88 grams during the experiment that we just calculated. What is your percent yield? So what you're going to do is you're always going to be given the number that you put on the top, the experimental. And what goes on the bottom is what your math answer is. And above our answer was this 102 grams. Okay? Multiplied by 100. So you're going to divide and multiply by 100 here, and you're going to get 86.3%. So that means our experiment was 86.3% accurate. We yielded about 86% of what we thought we were going to yield, okay? Which makes sense. It's very common not to yield exactly what you want. All right, so you will need to know this equation. The math is always going to be the number on the bottom, whatever your math answer is, and you are going to be given in the example or in the actual question the top number, okay? Now, because I know limiting reactant problems are difficult, I provided you with an extra example. I'd love you to pause the video and try this on your own. And then when you are ready, you can go to the next slide or continue watching the video and it will give you the answers, okay? So go ahead and pause and go ahead and do this problem. Going to go ahead and move down. So you can see we started with both amounts, the 15 grams of the NaCl and the 60.8 of the lead nitrate. We ended with the same product, and then we compared. We got 51 grams and we got 36. The one that is the lesser is our official answer. This is our answer here. That makes this NaCl our limiting reactant. That makes our PbNO3 our excess reactant. So then the question is saying which one is the limiting? The limiting reactant is our NaCl. It has to be a reactant. And the question also says how many grams of lead chloride, how many grams of the PbCl2 would be 36.4 grams. And again, that is the lesser amount produced. So here's our two answers.